some commentary on the Runge-Kutta exercises. Okay, so we have an initial value problem. The y dx just depending on x. That's so that question A actually works. If you have the derivative depending on x and y, the argument doesn't actually follow. Okay, this is just saying that the local errors are order h power k plus 1 and also related to the k plus 1 derivative. What does it mean to say that local error is O? So you don't just write O, you say this is what it means. Something is order something if its absolute value is less than a constant times that thing. So in this case, less than or equal to a constant times h power k plus 1. You could say the constant has to be positive, but that's not totally necessary. We've seen this argument done many, many times before in different contexts. So it's done all over the place. We'll just kind of look at it again. So the global error is the sum of the local errors, and these can be positive or negative. If you want to take a worst case scenario, so something bigger, make them all positive by using the absolute value. Now we can use the fact that they're all order h to the k plus 1, and then let A, say, be the maximum of these AIs. You could also, we've used KIs previously. I think I didn't use Ks here because you had K in another context, so it wasn't a good idea to use K. And then replace all these A1, A2 up to AN with the maximum of them. That's another worst case scenario. So you get n times A to the power, n times A times h power k plus 1. Now let xn minus x0 be L, and this should be a constant because you're interested, you have a final time. So that's a constant, and it follows that L, so the distance between these two is n step sizes, n h's. So that's the same as L, so you can write down that little n is L over h. And if you sub that in, you get that the global error is less than or equal to a constant, or even the absolute value of the global error is less than or equal to some constant times h to the k. That's exactly to say that it's order h to the k. What is the relationship between kth order Runge-Kutta and k plus 1 term Taylor method, and why is Runge-Kutta easier to use? So I think what I have down here is just kind of the green bit is just a bit of kind of thinking. So Euler is Runge-Kutta 1 because it uses one slope, and it's a two-term Taylor method because you've got previous and then step size times previous slope. That's the second term. And Hein is Runge-Kutta 2 and a three-term Taylor method. And what they both have is the same error profile. So for example, Euler method has global error. Well, that's not a great example because it's both Runge-Kutta 1 and a Taylor method, whereas Hein's method is not the three-term Taylor method, but it's the same error profile. So Runge-Kutta 2 and three-term Taylor method have the same error profile. Both global error have order h squared, so they have the same error profile. So they don't give you exactly the same answers, but like say if you reduce the step size by 10, your overall approximations are 100 times more accurate for both of them. But then why would you use Runge-Kutta? Because you don't have to calculate higher order derivatives. Now there's another thing there that could also be given as an answer. If your answer is a degree k polynomial, they'll both give the correct answer with zero error. But really what it's looking for, that these two things, kth order Runge-Kutta and k plus 1 term Taylor, have the same error profile. They'll give you similar answers and the same error profile. In Runge-Kutta is easier to use because you don't have to calculate a second derivative or higher order derivatives in general. And then another question we've seen a few times. So if k is equal to 3, so that tells us that we're using Runge-Kutta 3. I guess. Show that if you quarter the step size, the local error is reduced by a factor of 256. So the local error is order h to the 4. Hopefully that's written down below. Yeah, so the errors are order h to the 4, and the answer is that it's reduced by a factor of 256. If you want to show that, take the original error to be, say, it's approximately a times h to the 4. And what happens when you quarter the step size, that means divided by 4, you end up with this, the original error, the ah to the 4 divided by 256. And then the last question should be similar there. K equal to 4. So this is, you're talking Runge-Kutta 4. What's the effect on the global error? Now I've just shown that for kth order Runge-Kutta, so fourth order Runge-Kutta, the error is order h to the k. So this, the error be order h to the 4 as well. So that's there. And it'll be, if you half the step size, it'll be half to the power 4 reduced by a factor of 16. That argument kind of given again here. So the original error gets divided by 16 if you half the step size. Okay. Another question here. Consider an initial value problem, this time in terms of x and y. The common third order Runge-Kutta is given by this. Now it's important to understand here this thing in the green square. 1/6 times a couple of k's. So the k's are slopes. The f, the big F, is a formula for calculating the slope. Why? Because dy dx is the slope. So all of these k's then are given as big F at a certain point. So they are slopes. So K1 is a slope, K2 is a slope, and K3 is a slope. Now K1 is kind of the current slope at xi. K2, as it happens, if you look at the x argument, it's xi plus half a step size, so that's the midpoint. Just sneeze there. And then I think then this is the next point, so K3 is kind of, so yeah, so K1 is like it says previous or current slope, K3 is the next slope, and K2 is like the slope of the midpoint. And then the thing in the green square is averaging these by taking 4 of the mid slope, 1 of the current slope, and 1 of the next slope, and averaging them out. Okay. So then there's questions. So what does K1 represent? It just means the initial slope. I presume I have written that. Is the slope, is the initial slope of the solution, yeah. Because this is the initial point, and if you calculate big F, it's giving you the initial the slope, and it's the slope of the initial point, so it's the initial slope. K2, we've kind of discussed this. X0 plus h over 2 is the midpoint of x0 and x1. Yeah. This thing, y0 plus a half k1 times h, easier written as y0 plus h over 2 times k1. It's like an Euler predictor, because you have previous. It's like an Euler predictor for the midpoint. So it doesn't use the full step size, half the step size, and then the previous slope. So I think it's an Euler predictor for the midpoint, yeah. Therefore, what does K2 represent? An approximation of the slope at the midpoint, because this is the midpoint of x0 and x1, and this is an Euler predictor of the y value. So it's an Euler predicted slope at the midpoint. Euler predicted slope at the midpoint, yeah. Given that this is an approximation to y1, what does K3 represent? Well, just a similar story. This is the next x value, and this is, I don't know, what would you say, Euler predicted. It's kind of weird. It uses, like if you look at it, it's yi plus step size, and then the slope is 2k2 minus k1. Now, it's a weird kind of average slope because it uses it actually uses 2k2s, and then the question would be, why do you do, well, it's like 2k2s and then plus minus 1k1s, and so it's kind of weird. You don't have to average them. So it's a bit tricky, right? So it's a weird kind of average. So like, could I give an example of it? So like, if you're looking for the average of say 6, 7, 8, it's like saying, let's take 2 of these and take away 1 of these. It's a bit weird, but anyway, so you get 10. 6, yeah, you get 10. That sounds like absolute nonsense, doesn't it? I get 10. Anyway, well, for whatever reason, you are using one slope there. So that this thing, it's representing the slope at the midpoint. Excuse me, at the end point. Approximation slope at the end point, yeah. And then what does this thing in the green square? It's a weighted average slope. Okay. And another question here. 4-term Taylor method uses tangent cubic. Using the first 4 terms, we find this. To find the predictor of the tangent cubic, yeah. Okay. So describe how to find the second and third derivatives. So basically, this is the answer below here, A. We've got kind of an illustration in green, something that you wouldn't necessarily be writing on your script. So if you have a function of x and y, so for example, dy dx is x squared times e to the sine y, and you differentiate both sides with respect to x, you have to use implicit differentiation on this. And so when you do implicit differentiation and you differentiate stuff with y's, you end up with y's and dy dx's. So if you differentiate stuff with x's and y's, you end up with x's, y's, and dy dx's. But then the point is that you have a formula for dy dx in terms of x and y. So you can replace your dy dx in terms of x and y like that. And so you end up with something that actually just depends on x and y. And then you just do it again. So like you end up this. If you put the dy dx as x squared e to the sine y, if we put that as x squared e to the sine y, you'd have just x and y's, and differentiate again. You can see how nasty it gets. So this is 4-term Taylor method. This time is Runge-Kutta tree, which is like, it's all right. But using 4-term Taylor method is really a pain. Like, so anyway, if you put in this in terms of x and y and you differentiate again implicitly, you have x's, y's, and dy dx's. That's what this is saying. And again, you can put the dy dx in terms of x and y. So that's how you'd find the third derivative. Question B is very similar to C above. C is very similar to the above. Effect on global error, very similar. So the global error is h cubed. So if you half the step size, it's like half cubed, it'd be multiplied by 1/8, so reduced by a factor of 8. What order Runge-Kutta? Similar to 4-term Taylor. So again, you kind of figure it out. Runge-Kutta is 2-term Taylor, in other words, Euler. Runge-Kutta 2 is the same as 3-term Taylor. So Runge-Kutta 3 is the same as the 4-term Taylor. So you kind of figure it out. That's how I'd figure it out. So Runge-Kutta 1 slope is Euler method, and there's 2 terms. Previous is one. Let me just be clear here. How is Euler 2-term Taylor? Previous, that's 1 term, plus step size times previous slope. So it's Runge-Kutta 1 because it uses 1 slope, and it's 2-term Taylor also. Now Runge-Kutta 2 includes stuff like Hein and stuff, and that's like a 3-term Taylor method if you want to kind of match it. And so just kind of up the level, go from Runge-Kutta 2 up to Runge-Kutta 3 is the same as going from 3-term Taylor up to 4-term Taylor. And so the 4-term Taylor is the same as Runge-Kutta 3.